Allora, next speaker is Professor Kateryna Khalina from B. Berkin Institute for Low Temperature Physics and Engineering of the National Academy of Science of Ukraine, Kharkiv. She presents a talk titled On Boundary Controllability Problems for the Heat Equation with Variable Coefficients on a Half-Axis. Thank you very much.
Thank you very much. My name is Kateryna Khalina, and I'm representing my joint work with Larissa Fardigola on boundary controllability problems for the heat equation with variable coefficients on a half-axis. Consider the following control system on a half-axis. The heat equation with variable coefficients ρ, k, and gamma, the boundary condition of the Neyman type, and the initial condition. Here T is a positive constant, ρ, k, gamma, and W0 are given functions. U is a control, we consider it in L infinity of 0t, and we study controllability problems for this system. These problems are as follows. The first problem, we want to find a control U belongs to L infinity of 0t such that our control system may be transferred from the given initial state to the given target state at the time t. This is so-called controllability. And the second problem, for each positive epsilon, we want to find a control U epsilon belonging to L infinity of 0t such that our control problem 1, 3 may be transferred from the given initial state to the epsilon neighborhood of the given target state. Controllability problems for the heat equation began to be studied in the middle of the last century. They were investigated by many mathematicians, for example, by those you can see in this slide, and many other mathematicians. However, the number of papers dealing with the heat equation in bounded domains is much more than the number of papers dealing with the heat equation in unbounded domains. Moreover, a distributed control was considered in the most of these papers. In particular, it seems that these problems were investigated for the heat equation with variable coefficients in unbounded domain under the boundary control only in our recent paper of 2022. Note that a boundary control and a distributed control have a principal different nature. Thus, we consider the case of unbounded domain and the case of boundary control. In the mentioned paper of 2022, we investigated this control system, but with the boundary condition of the Dirichlet type instead of this type of boundary condition. The general methods applied in the present work are similar to those from the mentioned paper, but in this case, different spaces and operators are used. For equation data ρ, k, and gamma, we assume some conditions. We assume that ρ and k are continuously differentiable on a half-axis. They are positive on a half-axis. Their product is of the class C2, and the derivative of their product at the point 0 is 0. We also assume that this function sigma, that is the integral from 0 to x of the square root of this quotient of ρ and k, tends to infinity as x tends to infinity. Let Q1 be defined by this expression, and Q2 be defined by this expression. Finally, we assume that the function Q2 minus gamma lies in this intersection of L infinity and of C1, and we assume that this function is an element of L1 on a half-axis. Consider the even extensions of functions ρ, k, and gamma, and denote them by the same symbols, ρ, k, and gamma. Since we reduce our control system from the half-axis to the whole axis, we will always assume in our work that rho, k, and gamma are defined in R and they are even. Our control system 1, 3 on a half-axis, we consider modified Sobolev spaces HS for this S. These spaces are analogous of the Sobolev spaces, where the basic space L2 and the ordinary derivative d by dx are replaced by the weighted L2 space with the weight rho, and the linearly deformed derivative alpha d by dx plus beta, where alpha and beta are determined by rho and k. Now let us recall what is the Sobolev spaces. By HP, p equals 0 and 1, we denote the following Sobolev spaces. H0 equals L2, and H1, it is a space of phi from L2, such that its derivative belongs to L2. And these spaces are equipped with the corresponding norms. The norm for the 0 equals the norm in L2, and the norm for the 1 is equal to the square root of the sum of squared norms in L2 of phi and of phi prime. And we also consider the dual space H minus P with the norm associated with the strong topology of the adjoint space. Obviously, we have H0 equals L2 equals H0 dual. By this symbol, we denote the value of a distribution f from H minus P on a test function phi from HP for this P. And we have that the value of f on phi equals the inner product of f and phi in L2, in the case when f and phi are elements of the Sobolev space of order 0. Now let us define the modified Sobolev spaces. Let phi be a locally square integrable function. We consider its derivative in d prime. D prime is a dual space to D, and D is a space of infinitely differentiable functions whose supports are compact. By this symbol d rho k, we denote the modified derivative, and we define it by this rule. If in addition the modified derivative of phi is locally square integrable function and its derivative is also locally square integrable function, then we can consider the second modified derivative of phi. Since phi prime lies in d prime, then phi double prime also lies in d prime. And we have this expression for the second modified derivative of phi. Obviously, the m's modified derivative of phi equals the m's ordinary derivative of phi if rho equals k equals 1 for this m. Denote by L2 rho the weighted L2 space with the weight rho. And this space is equipped with the norm f. The norm f in L2 rho equals the norm of the square root of rho times f in L2. And now consider the modified Sobolev spaces for p equals 0 and 1. We denote them by this symbol, by this h. H of order 0, it is equal to L2 rho, and H1, it is a space of such phi from L2 rho that the modified derivative is an element of L2 rho. And these spaces are equipped with the corresponding norms. The norm of order 0 equals the norm in L2 rho, and the norm of order 1 equals the square root of the sum of squared norms in L2 rho of phi and of modified derivative of phi. And we also consider the dual space H minus P with the norm associated with the strong topology of the adjoint space. Evidently, H0 equals L2 rho equals H0 dual. By this symbol, we denote the value of a distribution f belongs to H minus P on a test function phi belonging to HP for this P. And we have that value of f on phi equals the inner product of f and phi in L2 room, in the case when f and phi are elements of the modified Sobolev space of order 0. And we can see in this slide that the modified Sobolev spaces with their norms are analogous of the Sobolev spaces with their norms, where the ordinary derivative is replaced by the modified derivative, and the space L2 is replaced by the weighted L2 space with the weight ρ. Let f lies in H0. Then its modified derivative lies in H minus 1. And we define it by this rule. It is easy to see that if ρ equals k, then phi belongs to the modified Sobolev space of order m, if and only if the square root of ρ times phi belongs to the Sobolev space of order m for this m. And if ρ equals k equals 1, then the modified Sobolev space and the Sobolev space are coincide. The modified Sobolev spaces have been introduced and studied in these two papers by my co-author, papers of 2015 and 2016. By HS with a head denote the subspace of all even distributions of functions in HS for this S. By a capital W and a capital W0 denote the even extensions with respect to X of small w and W0 respectively. And put small q equals q2 minus gamma. Due to our assumptions, we have that this function q lies in the union of these sets, but its derivative may have a jump at the point x equals 0. In our work, we prove that control system 1, 3 on a half-axis is equivalent to the corresponding control system in the whole axis, the system 4, 5. Now we can see in the heat equation that the partial second derivative of w with respect to x is replaced by the second modified derivative of w. And here we can see additional summons, the function q. And in this summon, we can see our control u and delta. Delta is a direct distribution with respect to x and corresponding initial state condition. A solution W of this control system is understood as a mapping of the segment onto the modified Sobolev space of order 1 with a head that has a first derivative with respect to t in a classical sense. And this first derivative with respect to t is a mapping of the segment onto the modified Sobolev space of order minus 1 with a head. And the initial state lies in H1 with a head. Due to equivalence of control systems on a half-axis and in the whole axis, we will further consider this control system for 5 in the whole axis instead of original system on the half-axis. Now we can give the definitions. A state W0 belonging to H1 with a head is said to be controllable to a state WT belonging to H1 with a head with respect to system for 5 in a given time t, if there exists a control U belonging to L infinity of 0t, such that there exists a unique solution W to system for 5, and this solution at the point t equals WT. And a state W0 belonging to H1 with a head is said to be approximately controllable to a state WT belonging to H1 with a head with respect to system for 5 in a given time t, if for each positive epsilon there exists a control U epsilon belonging to L infinity of 0t, such that there exists a unique solution W epsilon to system for 5 with U equals U epsilon, and the norm for the one of the difference between WT and this solution at the point t is less than epsilon. To consider controllability problems for system with variable coefficients for 5, we consider the control system with the simplest heat operator. It is the system for 5 with rho equals k equals 1 and gamma equals 0. It is system 6, 7 in the whole axis. V is a control. It is in L infinity of 0t. It is a different control from U, generally speaking. And the solution Z of this system is a mapping of the segment onto the Sobolev space of order 1 with a hat, and its first derivative with respect to t is a mapping of the segment onto the space, Sobolev space H minus 1 with a hat, and initial condition. Here, by HP with a hat, we denote the subspace of all even distributions of functions in the Sobolev space HP for this P. Controllability problems for this system were investigated in our recent paper of 2021, where we obtained some controllability results. To study controllability problems for system for 5 with variable coefficients, we use the transformation operator T that acts from the Sobolev space to the modified Sobolev space. It has been proved by my co-author in a two-mentioned paper of 2015 and 2016 that this operator is a continuous one-to-one mapping between the Sobolev spaces and the modified Sobolev spaces. In the present work, we prove that this transformation operator is a one-to-one mapping between the set of solutions to control system with constant coefficients and the set of the solutions to control system with variable coefficients. The application of the transformation operator allows us to extend the controllability results for system with constant coefficients obtained in our paper of 2021 to system with variable coefficients. And we conclude that control system with variable coefficients replicates the controllability properties of the control system with constant coefficients and vice versa. We also obtain in this work a relation between the controls U and V in this form. Here, a capital V depends on Z, the solution to system with constant coefficients, and on Q. And we prove that this capital V is an element of L infinity of 0t. As a result of application of the transformation operator, we obtain two main results of our work for a control system with variable coefficients. The first result: if a state W0 from H1 with a hat is controllable to 0 with respect to system for 5 in a time t, then W0 equals 0. And the second result: each state W0 belonging to H1 with a hat is approximately controllable to any target state Wt belonging to H1 with a hat with respect to system for 5 in a given time t. These results were illustrated by examples in the work, and consider one of them. Let t equals 1 second. Let the functions k, rho, and gamma are these functions in R. Let W0 equals 0, and let Wt equals this function in R. And we consider controllability problems for system on a half-axis, or for equivalent system on the whole axis, system for 5. Due to our second main result, we conclude that this initial state is approximately controllable to this target state at this time with respect to this control system. We apply the inverse transformation operator to our system with variable coefficients. Then we obtain a new control system with constant coefficients. Then we use the methods for constructing an approximate end state and control that we obtained in our paper of 2021 for this control system with constant coefficients. After that, we return to our given system with variable coefficients, and as a result, we find a piecewise constant control U depending on two parameters belonging to L infinity of 0t. For natural n, natural L, and L is greater than or equal to 2 times n plus 1. And we also find an approximate end state W depending on these two parameters belonging to H1 with a hat, such that the norm of order 1 between the difference between this given target state and this constructed approximate end state, this norm vanishes as the parameters tend to infinity. And here you can see some graphs of the difference Wt minus Wnl at the point t in some cases of parameters. The first blue, n is 3, L is 100. The second red, n is 3, L is 200. The third green, n is 4, L is 150. And the last pink, n is 4 and L is 400. As you can see, this difference vanishes while the parameters increase. All obtained results have been published in this paper of 2023, and thank you for your attention.
Thank you very much for your very interesting talk.